Let me start the stream because it doesn't happen. All right, great. Apologies for the delay. So what I'm pointing out now is where the solutions are posted. So they are posted if you go to our web courses in the files tab, same place I put everything. It's in the test one folder, specifically test one review, but boom, there it is. And it's right on top. Fall 25 Studio Test 1 answers. Great, you open this up. Now, this one is in the order of the concepts we've covered. Your all's tests were obviously not in that order on purpose. But yeah, I'm just going to scroll down to the Gauss's law, and it was basically, I think they're all going to be kind of in a row. All right, so we're going to go one at a time. It's literally number 9, 10, and 11. It's all Gauss's law. So I clearly showed I didn't prepare you all well for Gauss's law. Somehow, some way, something was not communicated. Like, again, something's off. So let's talk about them real quick. Number 9 says, and I'm actually going to put these on the PowerPoints. So I'm actually going to copy and paste them and work them out just so you have them as a reference. So DC circuits is going to go to the same place as the test scores. So a hollow metal shell, empty sphere with a radius of r has a net charge of Q uniformly distributed over its surface. What is the magnitude of the electric field at some distance r such that r is less than r? Anytime we have a Gauss's law problem, you should be drawing a picture of this. That is a good, on the test, you all have time. And with that time, go slowly, draw pictures, write equations, write the things. Sometimes when you immediately jump to an answer, that answer is wrong. By going slowly and carefully, that's how we make sure we don't make this mistake. So, hollow metal sphere. So we draw our sphere. Boom, there's our sphere. It's hollow. We then pick some spot inside of it. It says find the electric field at some distance r less than r. So in our picture, we draw our capital R. We pick our point, and then we draw our Gaussian shape. This is the skill that I think is maybe some of the source of it, drawing this Gaussian shape. And then what I'm also going to do is I'm going to draw where all the charge is. You can do this if you want to. Boom, there's all my charge. Remember that when we do Gauss's law, and this is going to show up in one of the other equations, E dot dA equals Q enclosed over epsilon naught. On the left side, we have E, and I'm going to be writing way more than I need to here. 4 pi r squared. Great, that side's done. Q enclosed. How much charge is inside of my Gaussian shape here? 0. There's no charge inside of it. Why? Because we're inside of it. So that was the answer to this one. What's my electric field? 0. Remember the Gauss's law, if you don't have any charge, you don't have any field. When you draw your Gaussian shape. So this really is getting at, I think, one of the major challenges, because this also came up in the free response, I'll point out. Q enclosed. It means Q inside. Inside of what? My Gaussian shape. You got to draw it so you can visualize. Like, that can be helpful. To draw how much charge inside my Gaussian shape? Big fat 0. None. So the electric field is 0. Great. So that's the answer to that one. The next one is the one immediately following this. The electric field some distance above an infinite charged plane is E naught. What is the electric field if I'm twice as far away from the same plane? So again, I'm going to put that on the slide for y'all. Boom, there it is. Now, anytime you're solving for something, again, it's good to know what you're solving for, and it's good to write the equation. If you want, you could draw a picture of this as well. That's kind of up to you. There's my infinite plane. My question is some point here, some point farther away. We're solving for the electric field as it changes. So we're going to want the equation for the electric field to an infinite plane. And it's sigma over 2 epsilon naught. Remember, y'all, sigma here is Q over A. So this is the one equation for the electric field I mentioned you're going to want to know. If I get twice as far away, what happens? Absolutely nothing. If I get farther away, how does my field change? It doesn't. Why? There's no distance in this equation. Nowhere in this equation does it have distance, r, d, any variable like that. So writing the equation can help to make sure that you're accounting for those things. What I think a lot of people did is they use this equation, KQ over R squared. That's for a point charge. They both solve for E for two different things. This one over here solves for the electric field some distance away from some point charge R. That is not this problem. So being careful of that. All right, and the last one. This one did involve math. A cylindrical wire with a charge distribution of 5 microcoulomb has a radius of 0.5 centimeters. What's the electric field? Some distance 0.6. We're going to do the same process that we did for the last problem where we drew the Gaussian shape. Boom. So we're going to draw. What are we solving for? Always good to keep track of what we're solving for. This is something, write the variable equals question mark. Very, very helpful to help avoid some problems. I'll point out one of the free responses where it would have saved a lot of people some headache. Maybe. So this one we draw our picture. Here's my rod. And then my Gaussian shape. I want some electric field farther. 0.6 centimeters is bigger than the radius. So I draw some Gaussian surface like this. There you go. And then we do, Gauss's law. E dot dA equals Q enclosed over epsilon naught. This is a cylinder. We're doing the sides of a cylinder. It's going to be 2 pi little r times L. Little r being the radius of my Gaussian shape, not the radius of my object. Boom, little r. Equals, my Q enclosed is going to be lambda times L, my charge density times the length. Rearrange this, and you get E equals lambda L over 2 pi R L epsilon naught. L's cancel. You plug in the numbers, convert your units, centimeters, not meters. Microcoulombs, not coulombs. And yeah, that'll get you the answer for that one. So again, the picture helps with all this and great. Okay, last couple things before I move on to the jokes. So the free response, the answers are all here. The reason that there's like these parentheses up here is because there's different versions. And so the answers for each version is shown there. That's as much as I can zoom in. This is one where I want to point out. This problem says, there's a couple things I want to point out here. One is the picture. I think a lot of people drew the picture wrong when they solved this. I saw this kind of commonly. I saw some people put R1 and R2 on the wire. How do we know they're not in the wire? It's this last sentence. Both points are above the horizontal wire. You got to be careful with these pictures. I actually included this wording because Angelina actually, when she was solving it, realized people might be confused where R1 and R2 is. So I actually added that wording from that. But yeah, so be careful if your picture's good there. But here is actually the major concern I saw. This is the most common mistake I saw with this one. It says, what is the potential difference? I saw a lot of people just solve for E. I saw a lot of people, if they solved this, they didn't know what to do. They just took the E equation, they put numbers in. So what do we do in this situation? How do we avoid making that mistake? What am I solving for? Write that down. Potential difference is V, delta V. If you realize that potential difference is delta V, if you realize that that's what I'm solving for, all you need to do is go down to the equations. Once you know what you're solving for, you go down to the equations and you just look at what equations might have, what I'm solving for, and what I have. So if we look here, delta V shows up in a few places. There's this Q delta V here. There's this V right here, and there's delta V equals the negative integral of E dot ds. Because I gave E in the problem, that kind of flags. That's probably the one we're going to use. So if you can identify what you're solving for, that really narrows down what equation to use. And remember, if you can identify what equation to use, that gets you most of the way there. Because the reality is once you have the equation, it usually goes pretty smooth after that. But that's the challenge. So anyway, there's that one. And then the last thing I want to mention, again, Gauss's law. Really common mistake I saw with this one. So this is the Gauss's law problem here. I saw a lot of people recognize Gauss' law, which was awesome. I saw a lot of people find, so to remind you all this problem, I have an insulating sphere, insulating solid sphere, and in the middle of that sphere is a little tiny speck of metal with some charge. I saw a lot of people do a great job of realizing the insulator. I need to do that like ratio. Saw that was great. How do you then include this charge in the middle? You just add it to that. So when I say charge enclosed, how much charge enclosed? Find how much charge is enclosed from the insulator. find how much charge enclosed for the metal, and just add them together. So what's the charge enclosed? It's the charge enclosed for the insulator. You do the math for that, boom. And then you just add whatever the metal is. If it's 3, put the 3Q. If it's 1Q, put the 1Q. If it's a 2Q, put the 2Q. This gets to the heart of what are we doing with Gauss's law? We're finding the charge enclosed, inside. How much charge is inside? If I got 2 objects, find the charge of each object and add them together. That's the key to this. Now, this is a really important skill for us because in 2 to 3 weeks' time, we're going to learn about Ampere's law, which is the magnetic field version of this. So instead of it being Q enclosed, it's going to be I enclosed, current enclosed. It's the same process. In fact, it's a little easier. Instead of E.dA, it'll be E.dl. But otherwise, it's going to look very similar. So we're going to be using that. So that's this idea of drawing the picture and finding what's inside said picture, what's inside said shape. That's a very important skill. It's going to show up again. Anyway, and then joke of the day.
Hello? Here's a question. Why did the man get fired from the calendar factory? He took a day off.
Yeah, it's good. All right. But yeah, look through these and feel free to look through these. They're all here. None of this is going to show up in test 2, but the final does have, this is good stuff to know because the final is cumulative. Anywho. Great. And this coming week, if you want to look at your multiple choice test, you can stop by my office hours, and I'm more than happy to show you your multiple choice test and what you missed. Obviously, the free response, they're not finished yet, so I can't show you your free response. There's 2/3 of them with Angelina, 1/3 of them with me. They're not done grading yet. So after this coming week, ideally, I'll be able to show you your free response if you want to see that. But there you go. All right. But again, I am very happy with how they went. And the free response I'm grading, it does look like a vast majority of you knew the process for these problems. And so it's going pretty, the free response grades are, the ones I'm grading are either going to be the same average as the multiple choice or maybe a little bit higher, but they seem at least around the same, which is great. And the 70s is really, really, really good. So. Anything to add or? All right. Since you're doing the great stuff. All right. So last class. What did we do last class? I taught you all 2 rules. I taught you all the junction rule and I taught you all the loop rule. The junction rule is what goes in must go out, specifically with current. The loop rule was that if we make a loop in our circuit, the voltages all need to add up to 0. Sometimes you go up, sometimes you go down. But if I end where I started, all my ups and downs cancel out. And we applied that to a problem. So we applied that to this problem. We made the 3 different loops in this problem. We made the junction rule for this problem. It was a grand time, so much fun. And so I think we also talked about power very briefly at the beginning. PIV, P equals IV. How much energy is converted every time you're using a circuit, light bulb, whatever it might be. How much electrical energy are you converting to something else? Generally a combination of things. All right. So today we just got a couple things to cover. We talked about resistors in series and resistors in parallel. And there's a nice little summary slide here. In series, you just add up the resistors. In parallel, it's the inverse. Now, I put the rules for capacitors on here just so you all can see that the rules are opposites. In parallel, capacitors add together. In series, capacitors inverse. You can see they're opposite to each other. This next test 2 is not going to have, I'm not going to have you combining capacitors on test 2. I'm not going to, but on the final, it'll have both. Now, there are going to be capacitors on test 2, but only in a specific context that we're going to talk about in just a second, specifically RC circuits. That's the only case that we're going to see capacitors. But you're not going to see multiple capacitors. It'll just be one. You'll see it in a bit. Before that, though, so we talked about the rules for adding capacitors in series and parallel. I want you all to try this problem. You do have all the skills necessary to do it. There is a few steps involved, though. This is a multi-step problem. So the question is, What is R1 in the following circuit if the current through R1 is 1 amp? My hint to you all is you're going to need to turn this into one resistor to solve this problem. To solve this problem, you're going to need to condense these resistors together. So use your skills to do so. And the other thing you need to remember is when you get one resistor, it has the voltage of the battery. So see if y'all can hash this one out. It's a fun little puzzle. And then once you do that, the power dissipated is really easy. But we'll do, for now, do part A. What's R1?
Oh, I got 18. I was doing the loop roll with the battery. And then these are 9 ohms.
Together, yeah. And so, and you have, you really
Since I
I
was
is just
1,
1.
yeah.
So you know that your total resistance is 9 ohms.
Yeah.
And you know that this is 2 ohms.
This is 2?
Oh, yeah.
This should
Did
be.
you math?
Oh, I did. Oh. That's funny.
Adding fractions.
That's a tough skill.
Huh?
I messed up my fraction.
Oh. So the key here is combine your resistors together. I got 3 resistors. Sure would be nice if there was just one resistor instead. How can I turn these 3 into 1? And there's going to be 2 steps to do that. You can't do it in 1 step. You're going to want to draw it. Every time you make a new one, draw the new circuit. If you don't draw it each time, you're likely to make a mistake. It's hard to keep track of what's going on.
Okay, so you guys did 9.
So
That is, yep, R net does equal R1. So now the question is, what else do you know about that resistor? There's two other variables to consider whenever we talk about resistance. We've got resistance, current. Good. So what do we know? We know the voltage of that of the one all together. 9. Good. Do we know the current through that resistor? There is a piece of information given in this problem. You have a resistance. What is it? The current through R1 is 1. Now look at your all's pictures. If the current through this one is 1, you turn them into one resistor, what's the current through that one? In series, what's constant? So the current through this one will be the same as when you turn it into one resistor. It'll be the same as when you do that one resistor. So then you have voltage, you got current. Yeah, that's the puzzle to this one. That's what makes this one more interesting.
Because like I used to sometimes after first I mean,
All right, so I've condensed them for you. If you're not sure how to condense them, call one of us over. Want to be able to help you well with that step, but that's how they condense. Now your question is, once you get to this point, if you haven't gotten there, call us over. But once you get to this point, great. Now what? How do I solve for it? I don't know what R1A4 is. I don't know what R1. And the trick here is to remember, anytime you have a resistor, there's 3 variables that you should be thinking about. There's resistance and 2 more that you should always be they're going to be involved in some capacity. What are those other variables, and how might I figure them out given the picture, given the information written in the problem? Good puzzle. Yeah. You got it. What gave you the last thing?
so this one.
So you got the answer.
Yeah. So I think these 2
Sure.
Yeah.
No, it's right by the power.
Yeah.
How did you know that?
Well, I didn't really do it. But you started nice.
Same in a specific in series.
Yeah.
So yeah, the current through these guys is the exact same through this one because they're in series. They're in parallel. Yeah, that lets you know the current, you know the voltage, you get that.
Oh. How do you
The answer is 7 ohms. If you got 7 ohms, good job. The answer to the second one is really, really easy. Once you have the net resistance, what's the equation for power? The cool thing about turning all your resistors into one resistor is if you can find the power through that one resistor, that is the power they use in the entire circuit. That's one of the beauties of this. Okay. But just to kind of walk through the last few steps here. So I wrote out most of this. The only things I didn't write out. So this R14, I kind of wrote that up here. If it's the only thing in the circuit, what voltage does it get? What's it connected to? A battery. If you all remember, if we like color code this, the top of the battery is 9 volts, the bottom volt is 0, so the voltage of the battery is the voltage of the resistor. If it's the only thing, it gets all the voltage. So that's useful. There's one more variable we should probably think about when it comes to this resistor. We got V, we got R. What's left over? Current. Sure would be nice to know the current. Now in the problem, it says the current through R1 is 1 amp. So that means the current through this resistor is 1 amp. What do we know about current in series? It's a constant. That means this other resistor also gets 1 amp. That means when you combine it into one resistor, it also gets 1 amp. So this problem kind of had two pieces to it. Do you know how to combine resistors together? And do you remember that current in series is a constant? Once you have those two pieces of information, I have voltage, I have I. Why is that useful? V equals IR. Rearrange that. R equals V over I. 9 divided by 1 is 9. My total resistance is 9. So through some nice easy math, if my total resistance is 9, 9 minus 2 is 7. Boom, that's that. And then what's the power dissipated in the whole circuit? Pick your favorite. PIV. P equals IV equals I squared R equals V squared over R. Pick your favorite variables. I'm just going to do PIV because it's easy. The current through the resistor is 1. The voltage is 9. So what's the power used in this circuit? It's just 9 watts. I don't need to find the power in every single resistor and add them up. I can just turn them into one resistor and it's equivalent. That's the whole point of combining the resistors, is you basically pretend like your circuit is this, and it acts the exact same as if it was. Very, very, very convenient. Another example of this is if you all take a multimeter, you can measure resistance. Say you have, I'll use an example. I was diagnosing my sprinkler system, and there's these things called solenoid valves. A solenoid valve, we're going to learn about solenoids in a few weeks. It's something that when you turn it on, it closes or opens the valve. It's just something that actuates when you apply current to it. It closes or opens. Now, one of the ways to diagnose whether your solenoid valves are broken is to measure its resistance. You're not measuring the resistance of every tiny little thing in the wire and adding them up. You just measure the whole resistance of the whole thing, and it has some value. And basically the rule was the resistance should be between these values. There's a pretty big range. It was like 40 to 60 ohms. If you're bigger than that, then there's probably some disconnect somewhere that's causing it not to work. If you're smaller than that, you have a short somewhere where it's ignoring some resistor values. Anyway, all that to say, you can treat big old elements of a lot of complicated things as one resistor, and that's much easier than a bunch of individual pieces. Great. Okay, so this is a good one. There's another one kind of on this. If you go to the problem sets, there's a problem where it's just basically a whole bunch of resistors. Combine them together to practice those skills. Fantastic. All right, one last thing that we got to get through in this PowerPoint, and that's what if you put them together, resistors and capacitors. So we're going to talk through what's going to happen. In fact, we have the time. I'm just going to build one real. So FET circuit simulator. I want capacitors. There's two different ones, so I need to make sure I find the right one. I've shown you all this before, but this is going to be very helpful for us just to remind us what it looks like. So this simulator, big fan of it, super, super useful. So we're going to build this RC circuit. What is an RC circuit? It's got a capacitor because it's C for capacitor. It's got a resistor. Boom, RC circuit. You got both pieces. Now, obviously, they're not connected. So we're just going to connect them real quick, and we are going to build the circuit in this picture. So we have a battery. We have a switch that can go from one form to the other. And there's going to be a charging case and a discharging case. And this simulator is going to let us actually see what's happening way better than any picture I could draw would look like. So first case, the resistor, I believe, is in line. Is there two resistors? No, just one resistor, but it's on that branch. Great. So it's going to be in line with this. So where's my switch? We're going to build two switches, one for discharging, one for charging. Boom. I should probably just look at my own computer. This is way too awkward otherwise. There's my capacitor. It doesn't really matter, all that. We're going to open this up so it doesn't charge yet. Wire. Great. Boom, there's that. I'm going to get another switch. Great. And this is going to be my discharging. Kind of, sort of. This needs to be moved. Don't worry. All this effort's worth it. Trust me. Without, because if I try to draw this, it's just not going to be as pretty. Okay. Cool. Now I'm going to make this resistor a very high value. I'm also going to make this capacitance a really high value, just so we can see things. We're going to learn why that's going to slow things down once we build our equation. So whatever, there's my ugly circuit. So here's what's, right now, nothing's happening. Why? There is no path, and we're going to use conventional current here. So it's going to, right now, there's no current flowing. Why? There's no path from the high voltage to the low voltage. Great. Let's also amp this battery up just so it lasts longer. When I connect this, what's going to happen? Oh, and this thing already started charged. All right, I need to discharge this real quick. All right, well, I guess it's discharged. That's weird. This should be empty, but that's fine. I guess it's got to, should be empty. Whatever. All right, when I connect this thing is charging up. Now notice, look at what's happening to my current as time goes on. It's charging. There's charges building up on that. I can't fill up this capacitor forever. I can't store an infinite amount of charge on it. As it gets more and more and more, the current slows and slows and slows. And I might have made it too big. It's taken a long time, but that's fine. It's getting slower and slower and slower, and you all can see that. And I picked the maximum value, so it takes, and eventually it will come to a stop. Eventually this current will come to a stop when basically this thing's full. At some point you can't put any more on it. It's pushing back. Now, if we measure the voltage of this, so right now my battery is a voltage of 66. If I measure the voltage of this capacitor, we can see it's increasing. It will stop when it gets to 66. Why? It'll have the same voltage of the battery, and they'll be equal and opposite and kind of cancel each other out. That's why charge will stop flowing. So it's going to take a while. It's kind of this, we're going to see what the curve for this looks like. But just trust me, it's going to do it. I'm not going to wait the 30 seconds to a minute for it to do that. Great. That's charging. Now, when I disconnect this, it stays there. Why? Where's it going to go? It's got no options. If you look at these negative charges on here, they're trapped. They can't go anywhere. There's no options for them. How can I give them an option? If I now connect this side, they discharge. The positive charges, quote unquote, are going to flow to this, and we call this the discharging case. So boom, RC circuit. You can charge it, you can discharge it, and something that's important here is it takes a set amount of time to charge. It takes a very set amount of time to charge. It takes the exact same amount of time to discharge. Why is that important? It's really useful for us to have things that take a certain amount of time. You could design a circuit that utilizes that so that when this reaches a certain voltage, something happens. Maybe a switch gets triggered and it discharges. What would be an example of this? So if we go to these slides, one of the examples of this is your windshield wipers. The way your all's windshield wipers work, you all have like that dial where you can kind of change how much, whether it goes really fast or whether it goes really slow. All you're changing is the resistor if it's an analog circuit. You're changing the resistance value. When you make the resistance value bigger, they happen slower. Your capacitor charges slower. And the way your windshield wipers work is when your capacitor reaches a certain voltage value, some switch gets triggered and it discharges. And then the cycle repeats again and again and again and again. So anytime you want to time something, this is very useful. Windshield wipers is something that happens after a certain point. Another one is a pacemaker. The whole point of a pacemaker is to have a set pace. These are very accurate timing devices. Very useful for triggering things every exact number of seconds. Electronics are very precise. We can design equipment that is very, 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 very precise in timing. And this is one of the ways. Another one is a 555 timer. That's an integrated circuit. Don't worry about that. Strobe lights is another one. When we get to AC circuits, we can actually filter frequencies. So that's something we're going to talk about a little bit later. So AC means it wiggles. The signal wiggles. Your phone is just collecting a bunch of wiggly signals, a bunch of wiggly voltages and things like that is what your phone's collecting. When you're getting a phone call, though, it needs to select a very specific frequency, and there's actually more complicated things that How do you do that? AC circuit, RC circuits let you select either low frequencies, high frequencies, or the band pass means like it does both. It selects a very narrow range. Whatever. All I'm trying to convince you of that RC circuits are everywhere. If I Google circuit boards, we're going to find a bunch of pictures. These are going to look like things that maybe you'd find inside a computer or any electronic device. Why am I bringing this up? No matter what picture I pick, you're going to see some cylinders. Those are capacitors. Every circuit is going to be like there's going to be capacitors involved. Resistors, every circuit has resistance. Remember, anything that current flows through acts as a resistor. There's also set resistor values in here. But literally any circuit board that you could possibly find is going to have resistors and capacitors on it. There was one I found when I was doing this. Was it? I don't know. Whatever. Look at any of these. They all got capacitors and resistors on them. Which ones are which? They take different forms and shapes and all that jazz. But long story short, we are going to do the simplest case. One resistor, one capacitor. Why? It gets way... You actually need a differential equation to solve this. But that's fine. I'm not going to make you do differential equations. I will make you do the loop rule for an RC circuit, though. What would be the loop rule equation for a circuit with one battery with a voltage of V, one resistor with a resistance of R, one capacitor with a capacitance of C? Assume a current that's shown in the picture. The current I is going clockwise. And remember when we do our loop rule, we both need to assign the direction of current and we got to walk through your circuit. We're going to walk in a clockwise loop. If you're confused how to do this, this is the same process that we did last class with these circuits. It's the same thing I'm having you do. Just replace one of these resistors with a capacitor. So if you're unsure how to do that, this is a great reference. Try it out. Build the equation. And I'm going to sling it to y'all to answer. Yeah, this is one you're going to want to write out, though, to make sure that you don't make any silly mistakes. As always, writing stuff out is good for you. It's good for everyone. It's good for me. Where did you start? Why did it go down? Why did it go up? That would make it want to go down as well. I want to go down by the voltage of the capacitor. How do I find the voltage of the capacitor? Alright, great. Rearrange it. We're going to go down. No. We hit the battery, go up or down. So very much
Yeah, it's like a.
All right, give me all 10 more seconds. And 5, 4, 3, 2, 1. All right. Whenever you do these circuits, every time there's a resistor, you should draw the current next to that resistor. That is something we're just going to, remember that was one of the first steps. There's that whole step-by-step process I wrote out in a previous slide. First step, draw the directions of current. Specifically, draw them next to your resistors. It just makes it easier. Next step, we draw the loop that we're going to travel. We are going to make a clockwise loop. Why? Because I just said so in the problem. Does it actually matter? No. It's not going to change anything as far as our answer mathematically is concerned. So great. Now we pick a spot in our circuit. We're going to start here in this top left corner, and we're going to start walking through this circuit. We're on a wire. Nothing happens. Nothing happens. I hit the resistor. Resistors. How do you know whether you're going up in voltage or down? Current flows downhill. That's the way to remember current. Current flows downhill from a high voltage to a low. So, current flows in the direction I'm moving. So am I going uphill or downhill? Downhill, great. We're going to call that VR, the voltage across the resistor. I'm going to leave it just as V for now, just to make a point. Great, great, great. We're going. We hit the capacitor. If I go across this capacitor, I start at the positive terminal and I go to the negative terminal. Did my voltage go up or down as I traveled through it? Down, great. Positive to negative is always going to be down. So minus the voltage of the capacitor. Walking. I hit the battery. I go from the negative to the positive. Up or down? Up, great. And I get back to where I started, so it all equals 0. Now we just plug in the equations. What's the voltage of the resistor? IR. What's the voltage of the capacitor? You all need to rearrange this equation. V equals C over Q. C over Q. Plus the voltage of the battery, which is just V equals 0. The only answer that matches this is not that one. That one's Q over V. Q over V is nonsense. You shouldn't have a V in there with a Q. The whole point was to write V in terms of the other variables. So that one was very careful. Did you solve for voltage? Great. All right. Now I am going to walk us through what we're going to do with this. And by we, I unfortunately mean me, which is not fun. I much rather when you all get to do these things, but it's a differential equation, and you probably haven't learned how to do that yet. All right. You do not need to know this derivation, but I just want to show you it didn't come out of thin air. All right, here's all we need to do. I equals dq dt. That is the definition of current. That is not anything new. That is like that. That's how we define current, the flow of charges. Now when I write this out, so I replace I with dq dt. We call this a differential equation. Why is it a differential equation? I have a derivative with respect to Q, and I have Q itself. So this is something you're going to take a whole class of differential equations where you do this. So what we're going to do is we're going to try to get dq and q on the same side. And then we're going to get dt on the other side. That's the goal here. What I'm about to do is not anything complicated, differential equate. It's just algebra. Literally, I'm just going to get all the q's together. Think of it that way. And then I'm going to put the dt on the other side. How do I get all the q's together? First, I'm going to multiply everything by c. Why? Because c is in the denominator, and I don't want it to be in the denominator. So great. cv minus dq dt times rc minus q. Just multiplied everything by c. Yay. Great. What's the next thing I'm going to do? I'm going to add that dq dt and the rc to the other side. So now I'm going to add that to the other side. So I get cv minus q equals dq dt r times c. Okay, just move and just do an algebra. Literally every step moving forward is just algebra. We'll eventually get to doing an integral, but it's not a hard integral. All right, cool. I need this dq. I need to get this dt to the other side, and I want to get this q to this side. So I'm going to kick the q. This q's over there. I'm going to kick this dt over here. So I'm going to get, and I'm also going to kick this rc over. So I'm going to get dt over rc. I just moved that to the other side, divided by rc, multiplied by dt. Equals dq over cv minus q. I'm just doing algebra. No step here has been anything crazy. Now what am I going to do? Integrate. How do I get rid of a dt? How do I sum up a bunch of dt's to turn it into t? Integrate. How do I get from dq to all my q? Integrate. Okay? How am I going to integrate this? I'm going to integrate from 0 to t. I'm going to integrate from 0 to q. R is a constant, C is a constant, C is a constant, V is a constant. You all can do this integral. Try it. It's good practice. It's not a hard integral.
A year ago, I said that. Absolutely great.
All right, y'all. If R is a constant and C is a constant, what's the integral of dt? T. Great. It's just T over RC. If you plug in the bounds, 0, 0. It's great. All right. What's the integral of CV minus Q with respect to Q? Negative natural log, good, of CV minus Q. Now, negative natural log of CV minus Q, but here's the problem. You got to put your bounds in. You got to put those bounds where Q is. Normally, we don't use the same variable, but just for the sake of it, I've done that. All right, so we have T over RC. I'm going to go ahead and move the negative sign over here for funsies. And I get natural log of CV minus Q minus natural log of C times V. A very useful identity that's good for you all to know is the natural log rules. When you subtract your natural logs, you can put them inside and just divide. So negative, I'm going to write this over here. This is a very useful rule for you all to know with natural logs. I've already actually, you didn't need to know it on the test, but it made things maybe slightly easier. T over RC equals natural log of CV minus Q over C times V. Great. How do I get rid of a natural log? You take the exponential of it, and I'm running out of room here. Again, it's kind of a long-winded kind of thing because I'm writing out every single step, but no individual step is that hard. It was a bunch of algebra and an easy integral. So great. We're then going to e to the negative t over RC equals CV minus Q over CV. What am I now going to do? Multiply this again, just more algebra. CV e to the negative t over RC equals CV minus Q. Solve for Q. You get Q equals CV. Oh, I lost the negative sign somewhere. We'll just see what happens. I think I lost the negative sign here somewhere. Oh, no. I'm good. I was like, what's going on? The Q I added to the... Okay, negative Q equals CV e to the negative t over RC minus CV. So Q equals CV. I'm just going to factor that out because I'm tired of writing it. 1 minus e to the negative t over RC. Woo! We did it. All right. And you know what would be real handy? To remember that C equals Q over V, and therefore Q equals C times V. So Q of T equals Q max times 1 minus e to the negative t over RC. You do not need to know this derivation. In fact, you don't even need to know this formula is on the formula sheet. Boom, there it is. It's the charging equation. We did it! First differential equation, maybe you've done. You don't need to be able to do the differential equation, but I wanted to show you it came from stuff that you know how to do. You know how to do loop rule. Maybe you're still practicing and learning, but that's when we did the loop rule. We had to do a differential equation, but hopefully I showed it wasn't too bad. All right, that's a charging equation. What does the equation look like? This is what it looks like. So this is the charging equation, where as time goes on, we reach some plateau where my charge kind of, quote unquote, caps out. We saw that in our simulation. It slowed and slowed and slowed and slowed. Great. How do you make the current equation? You take the derivative. If I say that's the current, you just take the derivative of that. That's not that graph. Where is it? There it is. The current decreases over time. Why? We saw that in our thing. It got slower and slower and slower and slower. Yay! All right. What if I'm discharging instead? You would do the exact same process, but with no battery in it, and you get this result. It's the exact same thing, except instead of 1 minus, it's just the exponential. It's exponential decay. If you all are looking at this and you're intimidated by this, what I want to remind you all of it, this is the same form as half-life. If you all took a chemistry class and it said like half-life population over time, it's the same equation for discharging. And in fact, in half-life, you still have a time constant. Our time constant, I do want to point this out. This little thing here is called tau. It's the Greek letter tau. It's where we get the letter T from, depending on, how letters formed and all that jazz. So something that you might see is that these equations written as Q of T equals Q max e to the negative T over tau. It's the exact same thing. If you ever have two constants, we just turn them into one constant. It's a really normal thing for us to do. But yeah, tau is R times C. If anyone ever asks you for the time constant, it's R times C. All right, then we just have one problem to practice this. All right, I got so RC circuits really are just, can you use those equations? If you can do a half-life problem, you can do one of these. A 50 microfarad capacitor initially uncharged is connected to a 300 ohm resistor to a 12 volt battery. What is the magnitude of the final charge on the capacitor? And then how long after the capacitor is connected to the battery will it be charged to 1/2 Q? How long will it take for the capacitor to be charged to 0.9 Q? The only thing I need to tell you all is that when this capacitor is fully charged, it gets the voltage of the battery. So that's my hint to you all for one of these things. When the capacitor is fully charged, it gets the voltage of the battery. That's why it stops charging, is it gets the entire voltage, and so the whole circuit comes to a halt. All right, try it out. you're unsure how to do part A, ask someone around you. It's very quiet today. See if someone around you knows, or ask one of us. You're free. Bet you someone at your table knows how to do it.
Oh, so like, so 50 times 12.
Y'all are part A.
Is that equal to that? Oh wow, it does. Okay, I was thinking that. Yeah. I don't know if we're going to the lab after this. Yeah.
It's written it. Yeah, no, I just didn't hear you. Y'all said it. It was so quiet I couldn't hear it. No. If I didn't respond to it, it means I didn't hear it. I don't just ignore it like people log in. So it's log into that. Not usually it's weird. Alright, great. You got voltage. You got charge. Is there any relationship between voltage and charge and capacitance? C equals Q over this. Trying to figure out. It's that easy. It's that easy. If you really want to use the charge to your equation, just make time infinite. And what does that do? E to the negative infinity is just the rest of it you will use the equation. The rest of it you will use this equation. Alright, are you all in part A? Oh yeah. Oh no, you don't need that. You have CV equals Q max. You got the equation right there. That's all you need. Yeah, if you know the voltage and you know the capacitance, you can find the charge. Yeah. If you really want to use this equation, all that happens is make T go to infinity. When will it be charged? And e to the negative infinity is 0. So you end up just getting Q equals Q max. So how do you get Q max if you voltage to the battery? If you had to know that it's when does it stop charging? When it gets the voltage of the battery. Yep. Yeah. All right. So again, for part A, all you need to know is these two things. Q max is what I'm solving for. V max. Okay, there's one more thing you need to know. You need to know that the voltage equals the voltage of the battery. And it sure would be handy if there was a relationship between voltage and charge for a capacitor. If only there was a nice, easy equation that related those two things. And a third variable. That's the number. All right, the next one you'll get to use the charging equation. And then for parts B and C, you've got to use the equation. I got the Alright, I haven't actually plugged in the numbers myself. This problem with the past. I'm hoping it's right.
I got like come up for part B.
Yeah, part C. Part B, you got the right answer.
Yeah, it's just a little bit different.
Okay. Does it put it rounds?
Kind of.
Of course it does. Yeah.
At least what I got.
Sure.
I don't know.
Let's see here. So you have that's a minus sign, right?
Oh.
So 0.9 minus 1 will give you negative 0.1. Yeah. Again, part B, it's always useful to identify what you're even solving for. I'm solving for time, but I'm solving for a very specific time. I'm solving for the time when Q of t equals 1/2 Q max. That is a thing that is true. So just put that where Q of t is. It's the half. Look at chemistry. You all did half-life. It's just like that. The equation's tiny different, but it's the same thing. Turns out you don't even need to know Q max. If you don't know what I mean, plug it in and you'll see that you actually don't need to know Q max to solve this problem. Just like when you do half-life, you don't need to know your population to solve for the time for it to happen. Yeah, write the equation you're going to use and start plugging things in. That's the key. If you're stumped, write the equation. Then see if you can start plugging variables in. The worst thing you can have is a blank paper. You just got to be careful to use the charging equation, not the discharging equation. You will get the wrong answer if you use the discharging equation for part C. Natural log. It is the, as weird as it sounds, it is literally just the inverse of exponential. That's why it's good. So E is just a number. E is 2 points. Like if you're going to be to 1, E is literally just a number constant. No, natural log is, so natural log is chosen because it's the solution. The equation natural log is the solution to the 1 over x integral. So that kind of like came from that. Now as far as what is, and then it turned out that what was the base for natural log is like this base E thing. So I honestly don't know the full history of it. But yeah, that's kind of the reason it's useful, is it's the integral of 1 over x. And E is just the base for it. So I forget the chicken or egg. Natural log, like what is natural log? Where does that come from? It's the integral of 1 over x. It's also like log, but instead of base 10, it's base E. But I don't know which came first. If they're like, we need a solution to the integral 1 over x, or if they kept finding the number E, and natural log was the opposite of that.
Oh, that asks the question if like was E discovered before?
Yeah. I don't know which one.
Or calculus.
I
think E's older.
I think E was discovered first, and then you have log, which is the solution to the power.
Yeah.
I also don't know how they solve for natural log. I assume it's an infinite. I think when your calculator does natural log, it does a Taylor series expansion of it, and that's what sine of theta does as well. So they just do ln of x equals I forget the Taylor series expansion, but they just go to a certain number of terms on it. And those terms are all just like powers of x. So you can actually solve it, because otherwise it's this arbitrary, like, what is it? So it solves like the first 5 terms of the Taylor series expansion. I don't know how many terms, right? I'm making it like. Alright, if you haven't figured it out for this, you just take this and you put it here. And then you solve. So you say 1/2, the question is, when do I reach 1/2 q? What a great question. All right, my final is 1/2 q. And then, look, the q maxes cancel, so I get 1/2 equals 1 minus e to the negative t over rc. So 1/2 minus 1 is negative 1/2. That's going to cancel with the negative in front of that, so I just end up getting positive 1/2 equals e to the negative t over rc. Do the natural log of 1/2. equals T over RC. So T equals RC ln 1/2. You plug in numbers and great. What do you do instead when it's 0.9Q? Replace 1/2 in the beginning with 0.9 and go through the same motions. But yeah, this is, again, I keep referencing Half-Life because that's just in my mind. This is what, I just remember doing a lot of Half-Life problems when I was in my undergrad chemistry class. So much so that I remember it now, which is saying something because I'm really bad at chemistry. All right, so there you go. Just to show you all the equation for part C. Part C is not going to be ln of 0.9. Do not put ln of 0.9. It's going to be ln of 0.1. Why? Because you do 0.9 minus 1. Go through the motions for part C to prove that this is true. You don't just put whatever the ratio is in your cat. You got to go through the steps to make sure you're doing it right. When you skip steps, that's when you accidentally make mistakes. If I'm constructing a sentence, I don't just say the first and last word of the sentence and say, that makes sense. You can fill in the rest. I mean, in this case, I kind of am, but. All right. So you can keep working on this if you want to. We'll go ahead and do our break for a few minutes, and then we're going to start our lab. Go ahead and join your lab groups. I need to make the lab in groups.
This is very interesting history. Like,
I assume they discovered E first.
yeah. Well,